welcome to the latest installment of the IGCSE 0606 Solution Guide series. In this video we will take a closer look at paper 1.1 from the May-June exam period of 2021. So without further ado, let's dive straight into it. In exercise 1a we are supposed to sketch a graph of the function y equals 5x plus 1 multiplied 3x minus 2 multiplied x minus 2, stating the intercepts of the coordinate axes. To figure out the y-intercept, we substitute 0 for x, and after doing so we should conclude that the y-intercept is 20. Next on, to figure out where the graph intersects the x-axis, we need to keep in mind that the result of a multiplication is 0 in case that at least one of its factors is 0. Since 5 is certainly not 0, the only factors that can become 0 are those three expressions in brackets. Each of those we will equate for 0, and rearranging those for x will provide us with the x-intercepts of the graph that's been provided. Moving on to part B of exercise 1, here we are supposed to find the values of x for which the graph contains values that are larger than 0, and this can easily be spotted through closely inspecting the graph. All of those blue shaded areas are located above the x-axis, thus larger than 0, and this occurs for the intervals for x being larger than -1 but less than 2/3, and this occurs again for the interval of x larger than 2 up to infinity. In exercise 2 we are required to find the integral of this expression here, and we should provide our answer in form a plus the natural logarithm of b, whereby a and b are rational. To do so, we will firstly rewrite the latter part of the expression inside of the brackets using the laws for powers. The first part can remain as is, since the integration of the expression 1 over x equals ln x, using the laws of exponents. Now we can apply the power rule to integrate the expression in brackets x minus 1 to the power of -2, while keeping in mind that we need to combine it with the chain rule. After simplification of this expression, we just substitute x for the upper and lower boundaries of the interval that's to be inspected. Since we are to provide the answer in form a plus the logarithm of b, we need to make sure that the expressions containing the natural logarithm need to represent it in a way that they contain the same base. Thus we need to replace 4 with the expression of 2 to the power of 2, since in brackets we are facing a natural logarithm of 2. Applying the properties for logarithms, we can then in turn rewrite the expression natural logarithm of 2 to the power of 2 with 2 multiplied the natural logarithm of 2. After simplification, we can conclude that the answer can be given in the form that was required. In this case, a being represented by the expression of -1/4 and the natural logarithm of b by the natural logarithm of 2. Next on to exercise 3. Here we are working with the polynomial ax cubed minus 9x squared plus bx minus 6, where a and b are constant and the polynomial has a factor of x minus 2. Furthermore, the polynomial has a remainder of 66 when divided by x minus 3. In part A, we are supposed to find the value of a and b. Since we are looking for two different unknown variables, in this case a and b, we need to use the information that's provided in the exercises in order to set up two equations, both of which are either rearranged by a or b in order to eliminate one variable, which will then at the end lead to us being able to find out the value for a or b first, and thereafter the value for the missing respective variable. Since we know that the polynomial has a factor of x minus 2, we know that p of 2 equals 0, since 2 minus 2 equals 0. Our second piece of information, that for p equals 3, the polynomial has a remainder of 66. So from there we will be able to set up two equations, and in both instances we will rearrange those equations for b. Thereafter we will take both of those equations and equate those with one another, and rearranging this equation for a will provide us with its value, which in this case is 6. This value can then either be inserted into the equation that was derived for p of 2 but it could equally done for replacing a in the equation that we have received for p of 3. In this case, I've done it for the former, and after having substituted a for 6, I came to the conclusion that the value for b equals -3. In part b of this exercise, using our values of a and b, which we have just found in part A of this exercise, we're supposed to show that p of x equals x minus 2 multiplied q of x, where qx is a quadratic factor to be found. So to find q of x, we can just rearrange this equation for q of x, leading us to q of x being the same of p of x divided by x minus 2. This means that we have to perform the following long division, and after doing so, we indeed receive a quadratic factor as stated on the outset of the exercise. In the final part of exercise 3, we are supposed to show that the equation p of x equals 0 possesses only one real solution. Since one solution was already provided during the earlier stages of the exercise, we just need to focus on finding the solution of the quadratic part of p of x. This can be done by making use of the quadratic formula. Since it says that p of x only possesses one real solution and x equals 1 already being that solution, we need to prove that the quadratic formula doesn't lead us to any additional solutions. To make sure of this, instead of calculating this entire expression, we just need to check the value of the determinant, which is everything that you can find underneath the root sign, which is also known as the radicand. Calculating the radicand shows us that it provides us with a negative solution, and since the square root of negative numbers is not defined within the realm of the real numbers, we can indeed conclude that p of x equals 0 indeed possesses only one real solution, which is x equals 2. Moving on to exercise 4, here it is stated that the first three terms in the expansion of this expression in ascending powers of x can be written in the form 27 plus bx plus cx squared, where a, b and c are integers. We are supposed to find the values of a, b and c. The key phrase here is the first three terms in ascending powers of x. Ascending here meaning that we start with x to the power of 0, continued by x to the power of 1, x to the power of 2, and so on. And these in our case already are the first three powers of x. Looking at this expression, we know that 27 is the coefficient of x to the power of 0. So in the next stage we need to figure out how 27 is related to a. Applying Pascal's triangle and knowing that we would multiply the results of this expression by 1 first, we know that 27 equals a to the power of 3 multiplied x to the power of 0, and since x to the power of 0 equals 1, 27 equals a cubed, and the cubed root will tell us the value of a, which in this case is 3. Here we can find the expansion of both of the brackets after the application of Pascal's triangle. As previously mentioned, the value for a is found by investigating all of the expressions in which a cubed and x to the power of 0 occur, and here it's just this single instance. To determine the value of b, we now need to investigate all of the factors deriving from multiplying a summand from the first bracket with the summand from the second bracket, providing us coefficients of x or x to the power of 1, both of which are the same. Those instances are highlighted through underlining them in orange. Here there are only two instances for which this is the case. A cubed, which is the same as 27 as already determined, multiplied by the expression -5 multiplied 1 multiplied x over 3, provides us with a product in terms of x to the power of 1. The same is the case for multiplying 3a squared x multiplied 1 over 2, providing us with a solution as required. Adding up those values provides us with the coefficient of x to the power of 1, which is -18. We proceed similarly in order to find the value for c. We apply the same method that we have done to determine b. The coding of the number represents the values that have been multiplied from each of those expanded brackets. Again, similarly to how we found the value for b, we simply add all of those results up in order to determine the coefficient of x squared, which in this case is -6. Next on to exercise number 5. We are provided here with two functions f and g, which are defined as follows. And in part A, we are supposed to find the range of f. This is done by equating the function for 0 and thereby finding its roots. After factorizing x, the roots are easily determined as being 0 and -4. Since the range needs to contain the smallest root value as well, which here is -4, the range of f must be equal or larger than -4. In part B of exercise 5, the same should be done for g, and remembering the properties of a regular e function, we should know that its y-intercept is 1 and the x-axis serves as its asymptote. So in this case here, the major thing that changes is that the e function is added by 1, meaning that its asymptote shifts by the same value across the y-axis. The only thing that the power of 2x does in comparison to the power of x is that this function is steeper, which does not influence the range of g. In part C of this exercise, we are supposed to find the exact solution of the equation f of g equals 21, and we should provide our answer as a single logarithm. Firstly, to determine the function f of g of x, we need to substitute all of the x values in the function f for the expression of function g. It can be seen that we are dealing with a biquadratic function, since the expression in both brackets are the same, the difference being that the first bracket is powered by 2 and the first bracket by 1, even though it's not visible at first sight. To solve this equation easily, we will substitute the expression in brackets with k and rearrange it for 0. At this stage we can apply the reduced quadratic formula, providing us with two solutions, namely -7 and 3. Now we need to resubstitute the entire thing to determine the value for x. In step 1 we equate -7 for the expression 1 plus e to the power of 2x, and after rearranging it for the e function we see that no results will be derived from there, since e functions do not contain negative values. Doing the same for 3, however, provides us with a positive result, so in order to move x away from the index, we apply the natural logarithm on both sides of the equation, since the natural logarithm is the inverse function of the e function. Applying properties of logarithms helps us in achieving a aforementioned goal. From here we just rearrange our equation for x, while not forgetting that the answer needs to be provided as a single logarithm. This can again be accomplished by making use of the properties of logarithms in conjunction with the properties of exponents. Thus our result should be the natural logarithm of the square root of 2. In part A1 of exercise 6 of this exam paper, we are asked to find out how many different 5-digit numbers can be formed using the digits 1, 3, 5, 6, 8 and 9, whereby no digit may be used more than once in any 5-digit number. To generally determine how many 5-digit numbers can be built by using each digit only once, we need to calculate the factorial of 5. As we are provided with 6 different digits though, there's a total of 6 different options to do exactly that. So we need to multiply 6 with the factorial of 5 and derive to the conclusion that there are 725 digit numbers that can be used using those 6 digits under the constraints mentioned in the exercise. In the second part of exercise 6a, we should find the answer to the question of how many of these 5-digit numbers are odd. Looking at the digits provided, we can determine that 1, 3, 5 and 9 are the only odd numbers out of those 6, meaning that our numbers can either end on 1, 3, 5 or 9. The only digits that are yet to be determined are the first 4 digits. To find a 5-digit number, we again are required to find the factorial of 5, which is the same as in part 1 of this exercise, and this needs to be multiplied by 4, as there are only 4 odd numbers out of those 6 that are provided. that can turn those 5-digit numbers into an odd number. In exercise 6a3, we are to determine how many 5-digit numbers are odd and greater than 60,000. Again, our final digits for the number to be odd must consist of the same odd numbers that we have used in the second part of this exercise. But here also there are constraints concerning our first digit, since it states that the numbers also need to be greater than 60,000. To achieve that, our leading number must either be 6, 8 or 9. Again, since each digit may only be used once in any 5-digit number, there are always 4 digits that can be used in order to occupy the remaining 3 digits, meaning we have 4 digits for 3 remaining slots. This can be calculated through 4 multiplied 3 multiplied 2. For the second digits there are 4 options, for the third digit there are 3 remaining options, and for the fourth one just 2 remaining options, and 4 multiplied 3 multiplied 2 can be represented by the expression of the factorial of 4. This then in turn needs to be multiplied by 4 for the case of numbers that are starting with 6 and are odd. The same is the case for 8. For numbers that are larger than 90,000 there are just 3 options, since 9 in itself is already an odd number, meaning that there are only 3 odd numbers left, which again fulfills the constraint that each digit can only be used once. Adding up all of those results provides us with the conclusion that there is a total of 264 5-digit numbers that are odd and greater than 60,000, taking into consideration that we can only make use of those 6 digits provided. In exercise 6b, we are dealing with the following equation, where we are supposed to find the value of n. Those elements here both represent combinations without repetition, formula provided. So in the first step, we are rewriting aforementioned combinations, applying the binomial theorem. In step 2, we just simplify the above expression. Thereafter we simplify 4 and 5 factorial, which delivers 5, since 5 multiplied 4 multiplied 3 multiplied 2 multiplied 1 divided by 4 multiplied 3 multiplied 2 multiplied 1. After simplification delivers the expression 5 over 1, which is the same as 5. On the right hand side of the equation, we just simplify the expression of 1 minus 4 factorial in the numerator and the denominator. In the next step, we simply multiply 45 by 5, and on the right hand side of the equation we can eliminate the term n factorial and pull the expression of n multiplied 1 plus n multiplied 2 together in the form of n plus 1 squared. Applying the square root on both sides of the equation provides us with 2 solutions, of which only n equals 14 is defined, since n is element of the natural numbers. In exercise 7a, we are provided with a diagram that shows the displacement time graph for a runner, whereby the value t can contain all of the values between 0 and 40 included. Part 1 of the exercise requires from us to find the distance the runner has traveled when t equals 40. To do this, we simply follow the movements of the graph along the y-axis. So after t equals 10, the runner has traveled 50 meters. Between t equals 10 and t equals 35, the runner has traveled another 50 meters. And for the final 5 seconds, the runner has traveled another 10 meters. Please be careful not to subtract 10, since it doesn't matter whether or not the runner traveled forward or backwards. Distance travel means the overall distance that the runner has covered. Part 2 of exercise A requests from us to draw the corresponding velocity time graph for the runner for the interval between 0 and 40 seconds on the axis below. In physics, velocity is defined as space divided by time. So looking at the graph from above, for the first 10 seconds, the runner has traveled a distance of 50 meters. Therefore, we need to divide 50 by 10. 50 by 10 equals 5. So for the first 10 seconds, the average speed of the runner is 5 meters per second. Thereafter, the runner changes directions for the remainder of the time, meaning 40 minus 10 equals 30 seconds. And during this time, he traveled a distance of 50 plus 10 meters, which are 60 meters. And since he traveled into the opposite direction, we need to calculate the speed accordingly as negative 60 over 30, which equals negative 2. In part B of the exercise, it is stated that a particle P moves in a straight line such that its displacement from a fixed point at time t is s. The acceleration of P is given by the following expression for t larger than 0. Given that P has a velocity of 9 when t equals 6, we are supposed to find the velocity of P at time t. According to physics, the relationship between acceleration and velocity is such that the integration of acceleration delivers us its corresponding velocity at the time t. Using a combination of the power rule for integration as well as the chain rule, we can conclude that the integral of the acceleration function can be expressed by the expression 2t plus 4 to the power of a half plus c. To determine c, we can use the following information. We know that at the time t equals 6, the velocity equates to 9, and exploiting this helps us in determining the value of c. So what we simply do, we substitute t for 6 and rearrange the entire equation for c, which provides us with the result that c equals 5. Putting both components together provides us with the desired velocity function. In part 2 of the segment, it is given that s equals 1 over 3 when t equals 6, and we should now find the displacement of p at time t. Again, applying knowledge from physics, we should know that the integral of the velocity function provides us with the displacement function. Here again, we will be applying a combination of the power and the chain rule for integration. After simplification of this expression, we will apply the same method that we have used in the previous step, namely using the information that is provided in terms of s and t. So here we just exploit the fact that for t equals x, the displacement is 1 over 3 meters. Rearranging this equation provides us with a value for d, and similarly to the previous part of the exercise where we had to find the value for c in order to determine the entire equation of the function for the velocity, we have to find t and again put both of those components together in order to find the function for the displacement in terms of time t. In exercise 8, prior to starting our work, we should not forget that we are not supposed to use a calculator in this question, meaning that we must show our work. Here it is stated that the curve has the following equation and that the x-coordinate of point A of the curve contains the value of the following fraction here. In part A, we are supposed to show that the coordinates of A can be written in the form p plus q multiplied 3 squared and 3 plus s multiplied 3 squared, where p, q, r and s are integers. To do that, we need to first find a way to rationalize the denominator of this fraction, which can be done by multiplying the numerator and denominator of the fraction by the so-called conjugate of the denominator, which in this case is 2 plus the square root of 3. This works for the reason that a plus b multiplied a minus b equals a squared minus b squared, and this expression here will ensure that our square root in the denominator will disappear. After applying this method, we can conclude that the original expression can also be expressed by the term 5 plus 3 multiplied the square root of 3. So what we have now found is the x-coordinate as requested, and in order to find the y-coordinate, by substituting this expression for x in the equation of the curve. In a first step, we just subtract 1 from 5. Thereafter we expand this expression applying the whole square formula, and prior to expanding both of those brackets we firstly simplify the expression of the second bracket, whereby 25 plus 27 equals 52. After expanding and simplification of the entire expression, we should conclude that the value for the y-coordinate can be represented by 18 plus 11 multiplied the square root of 3, which is in conjunction with the requirements as stated on the outset of this exercise. In part B of exercise 8, we are supposed to find the x-coordinate of the stationary point on the curve, giving our answer in the form of a plus b multiplied the square root of 3, where a and b are rational numbers. Our trigger expression here should be stationary point, which means that we need to calculate the equation of the first derivative of the function and equal it to 0. So here, in order to isolate x, we multiplied 2 with both summands inside of the brackets. At the same time, we bring positive 1 over to the other side of the equation by subtracting both sides of it with negative 1. From there, to isolate x, we simply divide both sides of the equation by the expression within the brackets. And then again, to rationalize our denominator, we simply multiply the numerator and denominator of the fraction with the conjugate of the denominator, which is 4 plus 2 multiplied the square root of 3. After simplification of the term, we can conclude that a stationary point can be found for x equals negative 1 minus 1 over 2 multiplied the square root of 3, which is in conjunction with the requirements of this exercise, demanding that the answer should be presented in the form a plus b multiplied the square root of 3, where a and b are rational numbers, which certainly is the case. Next on to exercise 9, where in the first part of part A of this exercise we are supposed to write the expression 6xy plus 3y plus 4x plus 2 in the following form, where a, b, c and d are positive integers. This can be achieved through factorizing. So looking at the summands 6xy plus 3y, we can see that both of those summands share a common factor, in this case being 3y, and for the remaining two summands they share a common factor as well, being 2. Here we can see that both of those summands share the same factor again, which in this case is the expression within the brackets, namely 2x plus 1. And after doing so, we receive an expression in the expected form. From there, we are now supposed to solve the equation in part 2 of exercise A. And looking closely at it, we should see that there is a resemblance between both parts of the exercise. The only difference being that x has been substituted by the expression of sine theta and y has been substituted by cosine theta, the rest remaining the same. So we can now rewrite this expression using our solution of part 1 of the exercise, whereby we substitute y and x for sine and cosine theta accordingly. Since for a product to result in 0, one of the factors needs to be 0, we can determine that either the first bracket equals 0 or the second equals 0. In the first instance, we receive the angle 131.8 degrees for a result. And since cosine theta is negative, we should know that cosine is negative in the second and third quadrant. Since this angle is located in the second quadrant, since it has a value that is between 90 and 180 degrees, we now need to determine its corresponding angle in the third quadrant. This is done through the properties of reference angles, which provides us with the result that the angle in the third quadrant is 228.2 degrees. In our second instance, we can see that sine theta equals a negative value, meaning that our angles must be located in the third and fourth quadrant respectively. And again, using our properties for reference angles, we will receive both of the angles required, one being located in the third quadrant and the other in the fourth, as to be expected. In part B of the exercise, we are supposed to solve the following equation within the interval of negative pi and positive pi, whereby phi is in radians. We are supposed to provide our answers in form of pi. Firstly, we will attempt to isolate the second expression, and after doing so, applying trigonometric identities, we can transform the expression second into 1 over cosine. After rearranging the entire equation for cosine, we are provided with the first solution, which is pi over 6. To determine the remaining solutions, we need to figure out the interval of this function, which can be defined by dividing 2 pi by 2, which delivers us pi. In the next step, we can find our first solution for phi by equating the expression 2 phi plus pi over 4 with pi over 6. Rearranging this equation delivers us the first solution, which is negative pi over 24. Since the interval of this trigonometric function has been determined as pi, we can receive our second value by adding pi to negative pi over 24, which results into 23 pi over 24. Since cosine possesses positive values in the first and in the third quadrant, we can employ reference angles in radians to determine our solution for the first quadrant. Since p over 6 is located in the fourth quadrant, as p over 6 is located in the first one, we can find the corresponding angle in radians by subtracting pi over 6 from 2 pi. So in this case 2 over 6, so in this case 2 pi minus pi over 6 will get us 11 pi over 6. Rearranging this equation for phi will deliver us the value 19 pi over 24, and we can find our final solution by subtracting pi from 19 pi over 24, which is negative 5 pi over 24. All of those values are as required within the interval of negative pi and positive pi. Coming to the final question of the exam paper, here we are provided with a diagram that shows a shaded shape. The arc AB is the major arc of a circle center O, radius 10 centimeters. The line AB is of length 15 centimeters, the line OC is of length 25 centimeters, and the lengths AC and BC are equal. In part A, we are supposed to show that the angle AOB is 1.70 radians, correct to 2 decimal places. The angle AOB can be determined employing the laws of sine, since the opposite of this angle can easily be determined, as we just have to divide the length of AB, which is 15, by 2. We can do so exploiting the fact that AC and AB are equal. Therefore, those two angles must be equal as well as those two lengths here. So the opposite divided by the hypotenuse delivers us 3 over 4, and with the assistance of our pocket calculators we can determine that the result is approximately 0.848. Since this is only half of the angle of AOB, we now need to multiply our result by 2, and we can see that the angle AOB is indeed 1.70 radians, correct to 2 decimal places, since 1.696 rounded accordingly delivers us exactly that result. In part B of this exercise, we are supposed to find the perimeter of the shaded shape, which consists of the arc line as well as BC and AC, whereby AB and EC have the same length. To calculate the size of the arc line, we will work with the following formula, whereby we plug in the values for the radius and theta, which are 10 and 1.70 respectively, providing us with the result that the arc line is 45.8 centimeters. To determine AC, we will be working with the triangle OAC, whereby OA is 10 centimeters and OC 25 centimeters, and both of those sides enclose the angle of half of OAB, which in terms of radians we have already determined. So now, since we are working with an SAS triangle, we will employ the cosine rule for right-angled triangles and plug in our values accordingly. Doing so lets us conclude that AC is approximately 9.9 centimeters. In a final step, we now just need to add up the lengths of the arc line and vice of that of AC, and can conclude that the size of the perimeter is 85.6 centimeters. In the final part of exercise 10, we are supposed to find the area of the shaded shape. The shaded shape consists of a circle sector combined with the area of a kite. To find out the area of the sector, we will work with the appropriate formula, and after plugging in the values accordingly, we know that the sector area is 229 centimeters squared. To find the area of the kite, we will again work with the appropriate formula, and after plugging in the values for the diagonals of the kite, which are 15 and 25, we can conclude that the area of it is 188 centimeters squared, and finally we just add up both of those values and conclude that the area of the shaded shape is 417 centimeters squared. I've been your host Marco from PlanetMaths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers.